This will be the third and last lecture on techniques of integration. I shall deal with two topics here. First, we'll learn how to do integrals of trigonometric functions. Now, of course, we've already learned how to do integrals of simple functions, but now we'll do this much more systematically. Secondly, we shall deal with now hyperbolic functions. Functions like sine, cos, tan, the relations that they obey, and then, of course, also how to integrate them. So, let's begin. In doing the integrals of trigonometric functions, it's going to be important to remember and know trigonometric identities. And I'll just quickly go over these just so that it's fresh in your mind. Cotangent of x is defined as 1 over tangent of x. Cosecant of x is defined as 1 over sine of x. And sec or secant of x is defined as 1 over cosine of x. These are just definitions, of course. In terms of content, the Pythagorean identity sine squared x plus cos squared x equals 1 is very important, and of course it's trivial to derive because what it is basically the geometry of a right angled triangle. And so if this is x and the hypotenuse is 1, then by definition this side is sine x, this side is cosine x, and so sine squared x plus cos squared x is equal to 1. This identity here and this identity here are derived by simply dividing this main identity, this one over here, by either sine squared x or by cos squared x. These two formula, which you must also remember, are important because they tell you that the sine of a sum of two numbers, x and y, is sine x cos y plus cos x sine y. If you reverse the sign of y, then obviously sine of minus y goes to minus sine y. So sine y is minus sine of minus y. And so that's why this sign over here changes. Similarly for the cosine of two angles, x plus y. These two you must remember. And you must also remember this one, sine of 2x is equal to 2 sine x cos x. That's very nice because you can sometimes take a product of a sine and a cosine, and if they're the same angles, then you'll just get sine of an angle which is twice as big. If you can remember all three forms of cosine 2x which are over here, that's fine. Otherwise, just remember the first line of this. Cos 2x is cos squared x minus sine squared x. And here you can put sine squared x is equal to 1 minus cos squared x and get the second form. Or you can put cos squared x equals 1 minus sine squared x and get the second form. Now, these half angle identities over here are not very important. In fact, it's just what is up above. If you write cosine of x equals 2 cos squared x by 2 minus 1, well, that's just this formula over here. And so I would not recommend that you remember this form or this form, but if you can remember it, it's good. What is absolutely crucial are the ones with arrows. So this, and this you must absolutely remember. Now let's proceed to calculating a few integrals. I'm going to do some very easy ones in the beginning. This integral here cries out for the substitution y is equal to sine x. If y is sine x, then dy will be cosine x dx. And obviously we have cosine x dx right over here. So we can write, instead of dx cosine x dy, Sine of x is y, so this is y to the power 4. And anyone can integrate this. This is y to the power 5 over 5. And so we get sine to the power 5, a fifth of that, x. Now, I could have added on to this a constant c, and that would have made no difference, because if you differentiate the right-hand side, you should get the left-hand side and the constant goes away. So we're doing indefinite integrals for now, but keep in mind that there's always a constant of integration c that comes with an integration. Let's proceed to integral of sine to the 5x. Now here, let me try the following. Let me put y equal to sine of x. But if I do that, then I will get dy is equal to cosine of x dx, and I don't see that anywhere. And this doesn't seem useful. So I'm going to try y equals cosine of x, in which case dy is minus sine x dx. And you see that over here I have minus sine x dx indeed, and that gives me minus dy. And then I have sine to the power 4x. But sine squared x is 1 minus cos squared x, and cos x is y, so I have 1 minus y squared squared. So what I've done is replace sine to the power 4 with what's over here. Now it's very easy to do this integral. I can just open this up. This is 1 minus 2y squared plus y to the power 4, which when integrated gives me minus y, and then plus 2/3 y cubed minus 1/5 y to the power 5. But of course we must write everything in terms of x, and so this is minus cosine x plus 2/3 cos cubed x minus 1/5 cos to the power 5x. And of course we could add on a constant, but I won't do that. That's understood. In very much the same way, we can do this integral. So put y equal to sine x, in which case dy is cosine of x dx. But we already have a cosine of x dx over here, and so this is dy. That leaves cosine squared x, but cosine squared x is 1 minus sine squared x, which means we have 1 minus y squared here. That leaves sine to the power 6x, which is y to the 6th. And now we can simply write this out as y to the 6th minus y to the 8th. And when we integrate this, we get 1/7 of y to the power 7. But y is sine x, and so that's sine to the power 7x. And the second term will be 1/9 of sine to the power 9x. This next example can be done in the same way, but it's faster if we notice that sine of x into cosine of x is half sine of 2x. And of course, since everything is squared over here, that is squared over there. And so we write this as 1/4 integral sine squared 2x. But sine squared 2x, we remember, is half. So the half and the 1/4 gives us 1/8. And inside we have 1 minus cosine of 4x. This comes from the formula that you were supposed to remember. Cosine of 2x is equal to 2 cosine squared x minus 1. And so we can now easily integrate this. This is x over 8. And when we integrate this, we'll get minus 1 over 16 sine of 4x. And of course, there's the constant of integration, but this is good enough. Now let's look at this integral where the angles are different. 7x over here, 4x over here. It'll be very helpful if you remember the following formula. Cosine of A sine of B is half of the sine of the sum of the two angles, A plus B, minus the sine of the difference of the two, A minus B. This actually follows from the formulae that you were supposed to remember, but if you can remember this as well as the ones for cosine, cosines, and sine, sine, that will help you do integrals like this more easily. Anyway, let's write this as half integral dx. The sum of the two will be sine 11x, and the difference will be 3x. Now, of course, you can immediately integrate this. When you integrate this, you'll get cosine, actually minus cosine, so it's minus 1 over 22 cosine of 11x, and here we'll get 1 over 6 cosine of 3x. So that was very simple, and it was made simple because we recognized immediately that it is this formula which is to be used. Now let's look at this one. Apparently this does not involve any trigonometric function, but we are going to introduce a trigonometric function that will make doing this integral much easier. So let me put over here, x is sine of y. Why am I doing that? Well, because if I have 1 minus sine squared y, that will give me cosine squared y, and then the square root of that is cosine y. Certainly, we see from here that dx is cosine of y dy. And now let's put that over here. So we have dy cosine of y, that comes from the dx. And this over here is itself cosine of y. So we get cosine squared y. Now, when we integrate this, we shall have to use the double angle formula. So here we have 1 minus cos 2y, actually 1 plus cos 2y. And now this is y over 2. And from here we'll get plus 1/4 sine of 2y. But of course, we want the answer in terms of x. If x is sine y, then y is arcsine or sine inverse x. So let's now get our final answer. This is half sine inverse x. And then here we have 1/4. Now sine 2y is to be expressed in terms of x, but sine 2y is, using the half angle formula, 2 sine y cosine y. Now sine of y is x. Cosine of y will be square root of 1 minus sine squared y, which means square root of 1 minus x squared. And so we have half, just writing this from above, and here half x square root of 1 minus x squared. So the sines and the cosines have disappeared from this part over here. They're present here, and they tell you that this kind of substitution was almost necessary in order to get our final answer. The integral of tan x can be easily done if we remember what tan x is. This is integral of sine x over cosine x. And now let me put over here y equals cosine of x. If I do that, then dy will be minus sine x dx. And so the dx sine x gets replaced over here by minus dy. So I have minus dy divided by cosine of x, which is y. And so this is just minus logarithm of y. But the logarithm of y is cosine of x. And that is the answer. Of course, you could add on a constant to this if you like. Next, look at the integral of tan cubed of x. Here we shall write this as, well, suggestively as the integral tan x into tan squared x. Tan squared x I'm going to write as sec squared x minus 1. So this is one of the Pythagorean identities, and it follows from sine squared x plus cos squared x is equal to 1. What I have then is this integral splitting into two parts. So there's tan x into sec squared x minus the integral of tan x. But of course, this second integral we have already done. In the first integral, let me make the substitution y is tan x. If I do that, then dy becomes sec squared x dx, and the dx sec squared up over there becomes just dy, and tan x is y, so that's dy y minus the second one, of course, which I'm going to write as what's above. So plus log of cosine of x. That's the second integral, this one over here. The first integral then goes to half y squared. Y is tan x, and so we arrive at our final result, half tan squared x plus log of cos x. We'll now do this integral of sec x, or the integral of 1 over cosine of x. There's a simple way to do it and a difficult way. The simple way, however, is a little tricky. What it involves is the substitution, which is not obvious at all, but let's make it. If I write y equals sec x plus tan x, then dy becomes sec x tan x dx. So that's the derivative of sec x. And then the derivative of tan x is sec squared x. If I take sec x common between the two, then I get sec x plus tan x. And that's exactly what we have for y. So I get y over here. And now that means that the integral that we have is just dy over y, because dx sec x, as you can see, is just dy over y, from which we get the logarithm, that's log of y, and by substituting y we get this final answer, sec x plus tan x. So it's a rather non-trivial result, but we got it so easily. And if we look at the next example, the integral of 1 over sine x, or cosecant of x, well, we can easily guess what substitution needs to be made, and in fact I will not do this. I will simply write down the answer, which is log of cosecant of x plus cot of x, and you can guess exactly what it is that we would have to substitute y for over here. The substitution y equals sec x is actually so useful that we can use it in many different situations. So if you take dy, which is sec x tan x, immediately you see that from here I can take away a sec x and a tan x, and so this becomes dy sec to the power 6x and tan to the power 4x. But this now is y to the power 6, and tan squared of x, as you remember, is sec squared of x minus 1. So this is y squared minus 1 to the power 2. Let's now open this out. This is integral then dy y to the 6, and opening this out gives you y to the 4 minus 2y squared plus 1, and that's the integral of y to the 10 minus 2y to the 8 plus y to the 6, each of which can be easily integrated. And in fact, let's write down the answer right away. This is then y to the 11 over 11. So 1/11th of y to the 11th, but that's sec to the 11th of x. Or let's write it this way. Then the next one will be minus 2 over 9 sec x to the 9. And the last one will be 1/6 of sec x to the power 7. So 7 over here. Before ending this discussion on the integrals of trigonometric functions, let me mention a very useful substitution. So if one defines y to be tan of x over 2, then immediately x over 2 is tan inverse y or arctan y, from which you get dx is 2 over 1 plus y squared dy. And using the double angle formulae that you saw at the beginning of this lecture, you can immediately show that sine of x is then 2y over 1 plus y squared. Cosine of x is 1 minus y squared over 1 plus y squared. Why is this useful? Well, suppose I have an integral of this form. Dx 1 over, let's say, 1 plus sine x. Then I can substitute the formula for sine x that you see above over here and dx, which is this. And this will then become the integral over y of a rational function, that means a polynomial over here and a polynomial over here. And then we can use the method of partial fractions that we studied in the last lecture. Now that's a rather simple example, and you could do it in another way too without using the above substitution. But then what if I had something like this, 1 plus sine x plus, let's say, 3 cos squared x. I'm just making this up. And then I could even square it or cubic or whatever. Again, by the substitutions above, you would get a polynomial on top, another polynomial at the bottom, and use that method of partial fractions. So there is a relatively systematic way of doing integrals where sine of x and cosine of x occur, and where they're not accompanied with square roots and so forth. Before we return to integration, we'll define new functions called hyperbolic functions. Here is the first example of that. This is hyperbolic sine. It's also pronounced shine sometimes, and this h over here stands for hyperbolic. This is defined as the exponential of x minus exponential of minus x, and it's divided by 2 for convenience. That's just the definition. Well, let's look at the values for different x's. If I take x equal to 0, then this is obviously 1 minus 1 over 2, that's 0. So sine of 0 is 0. If x becomes large, then sine of x gets dominated by the positive exponential, by e to the x, and so it approaches e to the x as x becomes large and positive. And of course, the exponential becomes infinity or gets very, very large. That's the meaning of that. On the other hand, if we look at values of x as x becomes very large but in the negative direction, so as x goes to minus infinity, then you see over here that e to the minus infinity will go to 0, but then here we have e to the minus infinity, that's very, very large, and so this goes to minus e to the minus x, and that goes to minus infinity because of the minus sign over here. Here's a very general fact. If I take sine of minus x, well, that's e to the minus x minus e to the plus x divided by 2. And that, of course, is just minus sine of x itself. So sine or hyperbolic sine is an odd function. And that means that the graph to the right and to the left will be the negatives of each other. We look at the graphs later, but you can already make out some things from here. E to the x is going to infinity and is going to minus infinity over here. So this is what you expect the graph is going to look like. And so it'll start from 0 and then go up. And on the other direction, it'll go like that. So we shall look at this later more carefully. But before going on, let me define another hyperbolic function, and that's the hyperbolic cosine, or what is called cosh. The only difference is that here there is a plus sign instead of a minus sign, and you can see immediately the difference is going to result in cosh of 0 being 1 plus 1 over 2, and that's 1 itself. So the graph of cosh of x is going to start from 1. It's always going to be positive because e to the x and e to the minus x are both positive. We see also that as x becomes large, then cosh of x, as x goes to infinity, will be dominated by e to the x, and that, of course, is infinity, and cosh of x will approach sine of x for large values. And of course, for the negative values, cosh of x will go again to e to the minus x, and that's going to plus infinity as compared to minus infinity for sine of x. So the picture is going to look roughly like this, that it shall start off from 1 and it's going to look like this, going to infinity on both sides. As compared to sine, cosh of minus x is going to be just e to the minus x plus e to the plus x divided by 2, and that's cosh of x itself. So cosh is an even function. That's very different from sine of x. Let me now also define a third hyperbolic function. And just like we define tan is equal to sine over cos, we're going to define hyperbolic tan, it's also called tan, as sine divided by cosh. And if you just put in the definitions from above, this is e to the x minus e to the minus x divided by e to the x plus e to the minus x. Of course, you can see that tan or hyperbolic tan of 0 is going to be 0. And then as x goes to infinity, tan of x is going to approach. Let's see what will happen over here. E to the x is going to become very large. E to the minus x is going to be very small. And so it'll be e to the x divided by e to the x. So hyperbolic tan of x will approach 1 as x becomes very large. Of course, tan of minus x, because it is an odd function divided by an even function, is itself going to be an odd function. On the other side, we see that tan of x will go to minus 1 as x becomes very, very large in the negative direction. Let us now look at the plots of the hyperbolic functions. Here is hyperbolic sine. You can see it comes up from minus infinity, is 0, and then goes off to plus infinity. Hyperbolic sine of x is clearly an odd function. Now let us look at hyperbolic cosine. You see that it comes in from plus infinity. It is 1 at x equal to 0, and then it goes off to plus infinity again. And now finally, let us look at the hyperbolic tangent. It is minus 1 at minus infinity, comes in from there, becomes 0 at x equal to 0, and then levels off or becomes asymptotically close to 1. Again, as you can see, the hyperbolic tangent is an odd function. It's easy to do the derivatives of hyperbolic functions. So for example, if I take the derivative of cos of x, that's the derivative of e to the x plus e to the minus x over 2. If I differentiate e to the x, I get e to the x. If I differentiate e to the minus x, I get minus e to the minus x. And so that is, of course, sine of x. If I take the derivative instead of sine of x, the only difference is that instead of this plus sign, I'm going to have a minus sign, and so I will have a cos of x instead. Now, it's very clear from all that we've studied that if I have two functions whose derivatives I know, sine of x and cos of x, I can get their ratios, or rather the derivative of their ratios. That ratio is hyperbolic tan of x, and you can easily check that that is cos squared of x. Now, instead of doing more differentiations, which are very easy, let me simply list various results. We've checked this and this and this. These three are to be remembered. On the other hand, these three can always be derived when necessary. Now, just for completeness, I'm going to write over here the hyperbolic cosecant, which is just 1 over hyperbolic sine. Here is the hyperbolic secant, which is 1 over the hyperbolic cosine. And this over here is the hyperbolic cotangent, which is 1 over the hyperbolic tangent. These are just definitions, but you ought to be aware of them. The hyperbolic functions obey a number of very simple identities, such as the one over here. This is easily proved by just putting in the definitions of cosh and sine. If I do that, then I have e to the u plus e to the minus u over 2, square that, subtract from e to the u minus e to the minus u over 2 squared. If I open this out, I get e to the 2u plus 2. That's because I have 2 times e to the u into e to the minus u, that's 2. And then there's e to the minus 2u divided by 4. And then we have to subtract from this sine squared u. That's e to the 2u minus 2 e to the 0. Well, so that's just 1 over there. And finally, e to the minus 2u divided by 4. So everything else cancels out. We just have 2 plus 2 over 4, and that's equal to 1. This second identity over here comes from dividing the first identity by cosh squared u. The third one comes from dividing the first identity by dividing by sine squared u. And these identities here and here come from simply putting in the definitions of cosh and sine. You can see that this over here is easily proved from the first one. Just take x equal to y equal to u. So take it in the first one over there and you get sine of x plus y, which is 2u. And that's sine u, cos u, and then that doubles up over here. So that's 2 sine u into cos u. Similarly, this one over here, cos 2u is cos squared u plus sine squared u. Now you will have noticed that this is very much like the trigonometric identities, except that instead of this plus sign, you had a minus sign over there. The same goes for the other identities in which, for example, over here, you have a plus sign instead of a minus sign for the cos and the sine. So the cos, sine and tan are very similar to the cos, sine and tan that we've studied in trigonometry. Let's now solve this question. If y is sine of x, what is x in terms of y? In other words, we've been asked to calculate the inverse of hyperbolic sine, which we write as sine inverse, and it could also be written as arcsine y. Let's begin by simply writing down the definition of the hyperbolic sine, which is e to the x minus e to the minus x over 2. And of course, that's completely equivalent to this formula, which is e to the x minus e to the minus x is equal to 2y. Let me multiply both sides by e to the x. So I have e to the 2x minus e to the x into e to the minus x, which is 1. And that's equal to 2y e to the power x. Now let's say that I call e to the x as u. So what I have then is u squared minus 2y u minus 1 is equal to 0. That's a quadratic equation which we can easily solve. The solution is u is equal to 2y plus or minus square root of now 4y squared plus 4 divided by 2. And now that is two solutions. I have y plus or minus over here. And let me tell you why I am not going to take the other sign. That's because u is e to the x, and e to the x is always positive. On the other hand, if I had taken y minus square root of y squared plus 1, then I would have got u to be negative, because this thing over here, what's under the square root, is obviously bigger than y. And so we have e to the power x is y plus square root of y squared plus 1. Now, you remember that if you take the log of e to the x, then that is just x. And so if I take the log of both sides, I get x is equal to log of y plus square root of y squared plus 1. Now let's understand this in some detail. So as you saw in the plots earlier, the hyperbolic sign looks like this. It comes in from minus infinity, goes off to infinity. And so if I was to ask what is, let's say, the value of x corresponding to a given y, so if this is y, then there is going to be only one x, and that's this x over here. On the other hand, if y is negative, then the value of x that will correspond to this negative value of y over here, so let me call that minus y here, that is also going to be negative. So whatever value of y you are given, there is a corresponding unique value of x. So we say that this function over here, the inverse function, is 1 to 1. In a similar way, one can get the inverses of all the other hyperbolic functions as well. We just did this one, but the cosh inverse is also easily worked out. But notice here that there is a restriction that what's in here, the argument x plus square root of x squared minus 1, has to be bigger than or equal to 1. And that's because if you remember the plot of cosh of x, it goes like this. So its minimum value is 1, and let's say that cosh had this value, then there are two possible values down over here. And in a similar way, you can get the inverses of the others, like hyperbolic tan inverse and Shek inverse and Koshek inverse and Koth inverse, etc. Now let's work out a few integrals using the ideas that we've just discussed. Let me make the substitution x is sine of y, in which case dx will be cosh of y dy. X squared plus 1, if we use the identity that we've discussed just a little while ago, the hyperbolic identities, well, that's cosh squared of y. And so this integral is then cosh of y dy, and 1 over square root of x squared plus 1 is 1 over cosh y. But that is just integral dy, which is y. But what is y? This is sine inverse of x. And so therefore, the integral that we are looking for is just sine inverse of x, which, as you remember, we have found to be log of x plus square root of x squared plus 1. And so we were able to do this integral rather easily using the trick of substituting hyperbolic functions. Well, now let's go on and do another integral. Square root of x squared minus 1. Now let me make the substitution x equals cosh of y. And you'll see why this is a good idea, because dx then becomes sine of y dy. And if I looked at square root of x squared minus 1, so let me look at x squared minus 1 now. That is cosh squared y minus 1, which is sine squared y. And so taking the square root, this becomes dy
sine squared y. But now we can use the double angle formula that we had discussed earlier. And this is now half of cos 2y minus 1. But this is an integral that we know how to do. This is 1/4 sine of 2y minus half y. Sine of 2y is 2 sine y cos y. So that's half sine y cos y. And that's half y as before. Now x is cos y, so we can substitute x for this over here. But what about sine y? Well, that's easily done. That's just the square root of x squared minus 1. And so we have half x square root of x squared minus 1 minus half y. But y is cos inverse of x. And so that is the answer. As our final example, we shall do this integral, but I shall do this in two different ways. First, using the method that we've already used many times now, I shall make the transformation x is hyperbolic tan of y, in which case dx will then be dy over cos squared y. Now 1 minus x squared is just 1 minus hyperbolic tan squared y, and that is 1 over cos squared y. So this integral then becomes just dy. That's because when I put in dx equals dy by cos squared y, this cos squared y is then cancelled by this one, because that's 1 over 1 minus x squared. And so this is just y, and y is, from what we have up above, is the inverse hyperbolic tangent of x. So that's the answer. It is completely correct. But now let me do this integral in another way. And so let's use the method of partial fractions that we had discussed earlier. This is 1 over 1 minus x into 1 plus x. And so I can write this as you can see very easily, 1 over 1 plus x, then minus 1 over 1 minus x. Well, actually, 1 plus x over here. Okay, so now I can integrate this 1 over 1 minus x squared, and what I get is half. Now the integral of 1 over 1 plus x is log of 1 plus x, and the integral of 1 over 1 minus x is minus half log of 1 minus x. And so if I wish to combine these together, then this becomes log of 1 plus x divided by 1 minus x. So here is the answer I get doing this integral in another way. Now they seem different, but they're obviously not, because tan inverse x is exactly this. And you can verify this for yourself, or just look at the tables of inverse hyperbolic functions that I showed you earlier. Here is a list of derivatives of the inverse hyperbolic functions. This is not for you to remember, but just for you to look at. And indeed, if I take the integral of both sides, then from this one, for example, I'd get dx 1 over square root of x squared plus 1 is sine inverse x. That means that if I differentiate this, I should get what's in here. And indeed, that is true from here, etc. So for example, here I would have dx, the integral of this thing, x into 1 minus x squared. This would be sec inverse x, etc.
If you have followed these last 3 lectures on techniques of integration, then you have pretty much learned all the general tricks that there are. However, you cannot become an expert until you do problems and exercises yourself. And if you do that, then you will become unbeatable.